Okay, so now let's kind of get into the analytics of the reliability analysis. And what we really need to do when we're doing this is we need to basically know all the different contingency events, all the different fault types, if you want to think about it that way. And we need to know where they're at and what's going to be the failure rate associated with each event, right? And so we need all the locations. Sometimes we get that from what's called a contingency map. We need to know the failure rate associated with each one as far as events per year or events per year per mile. And what we're going to do is for each event, we're going to simulate what's the response of the system as it relates to the outages it's going to cause. And some events, this could get pretty complicated. But basically, we need to know how the protection is going to respond as far as isolating the fault. Then what we're going to do for each of these different responses, and we're going to have this characterized by customer outage minutes, we're going to weigh the impact of the failure rate. And so if the failure rate's pretty low, then it's not going to have as much impact as, say, the failure rate's high. And then I just go back to step one and I just basically choose the next event. So if there's like 1,000 different possible events that could happen, I've got to look at the response to each one. And so you can see that we're not going to be able to do this manually for large systems. We're going to have a computer program to do this for us eventually. But what I can actually get from this is I can figure out for a given year, once I have all these different events simulated and I have the failure rates, is I can figure out, well, what's going to be the average number of sustained and momentary interruptions I'll have per year. What would I expect to have for interruption durations for each component in my circuit? So how long is customer A going to be out versus customer B? I can know the number of times protection and switching is going to operate per year. I can have these indices worked out for SAIFI and SAIDI. And so this is going to be somewhat of a brute force approach. And the other thing you need to keep in mind when you're doing this is these failure rates are averages over a long period of time, maybe like 5 or 10 years. So this won't tell you exactly what's going to happen next year, but it would tell you, like, on the average, what you could expect to see for a long enough time duration, like maybe 5 or 10 years. So the other thing we need to do when we're doing this type of analysis and trying to figure out the system response is we have to make some assumptions about what happens after the fault regarding system reconfiguration. Because there's going to be crews involved in this, there's going to be maybe some automation involved in this. And what I've got is I have a scenario, just as an example, that shows what you'd have to consider for fault location B. And so what we have is we have a primary source, S1. We're going to have the fault, and we're going to have to isolate this fault. And then I've got options as far as closing switches, and maybe I can backfeed some of this load from an alternate source. So the first thing you need to do when the fault occurs is you need to isolate that damaged section. And so that would mean going out here and opening up a couple switches on the source side of the fault and also on the load side of the fault. So we have to isolate the fault. The other thing you would do is, even though the customers on B can't receive any power because they're on a faulted section, what you could do is once this is open, if this circuit breaker is tripped open, you can close that circuit breaker. And for the customers at location C, what you can do is if you have this switch opened, you could actually then close this switch, and these customers at C could be fed from S2. And so you have to make some assumptions for how the restoration is going to take place, because this all factors into outage minutes, right? And A and C are going to maybe see some outage minutes, but that actually can be mitigated. They're doing some switching, where B, they just have to wait till that section gets repaired, right? The other thing you have to do too is if you're looking at backfeeding, what also goes into this process is you have to make sure you don't have under voltages and you don't have overload a piece of equipment. We're not going to get into this, but for our examples, but on a practical side, this is what you'd have to double check as well. So there's a lot of different things you have to look at, a lot of different things you have to consider for each contingency, right? So let's suppose we're looking at just one contingency, what would you have to consider in this case? Well, first of all, what we would have to do is we would have to know where the contingency is going to be at in the circuit, all right? And then basically model this somehow in some type of a circuit representation. And this could be due to a fault. It could also be due to equipment failing open, all right? So a lot of times we consider faults because that's probably more common, but you could actually have like a phase conductor break open, doesn't necessarily even cause a fault, but it can cause an outage downstream. Okay, so what's going to happen once a fault occurs? Then a relay is going to see that, and the relay a lot of times is going to attempt to run the circuit breaker through a reclosing action to try to clear it in case that turned out to be a temporary fault. And so right after the contingency occurs, then you're going to have some type of reclosing action for usually of an upstream breaker, not all the time, but usually. You may also have associated with the reclosing action what we call automated sectionalizing. And so you could actually have some other switches that not going to be fault breaking switches, but other switches that may operate in order to try to isolate the faulted area. We're not going to get into that in this class. It's kind of a complicated scenario. But when you're doing reclosing actions, there might be some downstream automated switches that could actually open during the reclosing sequence in order to help clear a fault. And then if the recloser or the breaker operating in reclosing mode can't clear the fault, then what happens is we're going to get a lockout. So the circuit breaker or the recloser is just going to pop open, and then everything downstream is going to see a sustained outage. Now, after that, you might be automated switching. So if we have remote controlled switches, we can operate those switches to restore customers. Maybe if we don't have the automation, we have to wait till a crew goes out there and operates the correct switches as well. And then once you've restored as many customers as you can, then you would have to have a repair on the bad section. And so this would take like maybe 4 to 10 hours or so in order to fix that fault. I didn't have it listed here, but then once you repair the fault, then you'd have a sequence of actions you'd go through in order to put things back to normal. But that usually occurs pretty fast. Okay, so all these different things, when we're looking at the response due to a contingency like a fault, we have to kind of model all this in order to figure out what's going to be happening as far as reliability is concerned. You'll see when I work through this example, this thought process. So I'll go through a real quick example now, and when we do the part 2 video, I'll spend a lot more time working through these different examples. So we'll start off first by looking at doing some basic calculations, but then in part 2, we'll get into fuse savings and doing fault isolation through like manual switches, doing sectionalizing. We'll talk about doing backfeeding and things like that. But first, let's kind of start with something pretty basic. And so what we're going to be assuming is we're going to just be calculating these 3 reliability indices, the SAIFI, the SAIDI, and the MAIFI, and these are the definitions for those. And then the input reliability numbers we're going to be just using for this will be the lambda values, the failure rate numbers for temporary and permanent faults on overhead, as well as a passive failure where something just fails open, doesn't cause a fault, but just something that fails open. As far as the times that we'll be using for repair and switching, we'll have an MTTR. This is the time it would take to repair the component. And then we're going to have an MTTS, which is the time to do a switching action. And the first example we'll look at is something really very simple. Simple distribution feeder with a circuit breaker. It's got three sections, three line sections. There's a load A and a load B, where those are characterized by different customer sizes. And line 3 has a fuse. All right. So we'll start with something real basic. The other thing we'll assume in this case is even the circuit breaker has reclosing, it's not going to coordinate with this fuse in order to do what's called fuse savings. And so if I have a fault on this circuit breaker, then I'll assume the circuit breaker is going to operate. But if I have and it'll actually reclose back in and attempt to clear the fault. But if I have a fault on line section number 3, even though it's temporary, that fuse is still going to blow, right? Because there's no fuse saving set up to coordinate the reclosing action of the circuit breaker with this fuse. So later on, we'll consider the fuse savings for this case, but now we'll just kind of assume that we don't have any fuse savings. So this is the reliability data for this particular scenario. I got the 3 lines. They have line lengths in kilometers. The fuse, the circuit breaker, and the source, they're just going to have time to switch. And so in this case right here, we don't have distances associated with these elements. And then you've got these failure rates in lambda T and lambda P correspond to temporary and permanent failure rates, and lambda OC is the open circuit rate. And so these are all going to be in terms of per year per kilometer. And then you have time to repair, and you have like time to switch. And so what time to switch would be for a fuse would be if I had to send a crew out into the field to replace a fuse element, given that we had like a temporary fault out there, it's going to blow a fuse. I still have to have a crew go out there, repair and replace the fuse. So the time to switch in that case is actually the time it takes to go out there and just put a new fuse element in. We're also going to have different customer counts for the different loads, and you're going to see how this kind of plays into the index calculation. So what we want to find for this case is we want to figure out what are going to be the number of momentary interruptions and number of sustained interruptions, what's going to be total outage duration. From these numbers, we're going to calculate SAIFI, SAIDI, and MAIFI. And then I can also get as a side calculation the number of operations for my switching devices like the circuit breaker and also the fuse. All right, so again, our calculation strategy is going to be, and this is kind of broken down a little bit more for this particular case. First, I need to know what are my different contingencies. I put together what I call this contingency map that basically kind of highlights where all my different faults are going to be at. And then I'm going to first process the temporary faults. And for each temporary fault, I'm going to look at the response. And I'm going to sum all this up where I have a sum net effect for all my temporary faults. Then I'm going to process all the permanent faults, one for each line segment. I'm going to find the response to each of those. And then I'm going to sum up the contribution to the permanent faults. And then finally, I'm going to process the passive failures. I've got 3 temporary faults in this case for the 3 line sections. I've got 3 permanent faults for the 3 line sections. I've got 1 passive failure on just 1 line segment. So I've actually got a total of 7 events that I need to model in this whole process. Okay, and that's shown in this particular diagram. Line section 1, I've got a permanent and temporary fault to consider. Line section 2, I got a permanent and temporary fault case to consider. Line 3, a permanent temporary. And then for the line section 3, I've got a passive event I need. So that gives me the net 7, right? All right, and what I'm going to do when I go through and get the numbers for each event to make it easier for me to add everything up at the end is I'm going to put the results into this table. And this table is a table I set up in a spreadsheet. And so these are the 7 different events. And for each event, I'm going to figure out, well, how many times is this going to occur per year? Is it going to be involving a circuit breaker operation or lockout? What impact does this have on each customer, on customers A and B? And then I'm using this just to give me a convenient way of doing the bookkeeping and getting the grand total. So this is really kind of a accounting problem in a way, where I just need to make sure I do all the bookkeeping. And for each event type, I know what's going to happen, that I can add all this up to get a grand total. So first thing we do is, we figure out, well, how many times these events are going to occur per year in each section. In order to get that, what I need to do is I need to take the length times the failure rate. All right. So if we're looking at line section number 1, and if I have a temporary failure rate of 1 per year per kilometer, if I have 1 kilometer, then I'm going to have one of these events per year, right? Do the same thing with permanent fault, I get 1 per year. Now, if I look at line 3, I've got a temporary failure rate of 2 times per year per kilometer. I've got 2 miles. So if I multiply that out, I get 4. And so I see what I have for temporary faults for line section 3 is 4 faults per year. And note I'm kind of rounding off the numbers in here just to make the number crunching easy to do. And then just make it easier for me to process all this information, I'm also putting the mean time to repair in here. So if I have a permanent fault, this is going to be the time it's going to take to deal with that. So in general, these numbers here do not have to be integer. When you're doing the stats on this, I mean, you could have it, instead of being 1 fault per year, it could be 1.357 faults per year. That's okay. Because again, we're talking about an average number of faults per year we expect to have. So what we do then is, given we've mapped out how many times we're going to have these events per year, then I just simply go and look at each event by itself and look at the response of the protection system. So this is why we have to know something about system protection. So if I have a situation where I have like 1 temporary fault that's below the circuit breaker, what the circuit breaker is going to do is it sees the fault, it goes through a reclosing operation, closes back in after a certain period of time. And if this is a temporary fault, then service gets restored. And so what this results in is 1 momentary outage. When the circuit breaker operates in the reclosing mode, customer B will see 1 momentary outage, customer A is going to see 1 momentary outage. We'll basically assume that the outage hours is going to be 0 in this case. I mean, if you really wanted to count it, it's going to be in terms of cycles. But typically for these sustained event indices, we don't count this, right? So I usually don't count an hour associated with this because it's just simply a momentary event. Same thing for line number 2. If I have a temporary fault, circuit breaker goes through a reclosing cycle. If the fault's clearable, then everything goes back to normal again. Again, I get 1 momentary outage for customers A and B. Now for C, we're going to have a different scenario. So I got a temporary fault. The problem is that we don't have the fuse saving set up where the circuit breaker operates before the fuse blows. Basically, this is going to have a small value of fuse in here. As soon as that temporary fault happens, that fuse is going to blow. So, and that's the case, a temporary fault, even though the fault's temporary and could have been cleared by a breaker operation, it doesn't happen because the fuse blows first. And when the fuse blows, we have to send a crew out into the field to deal with this. I'm going to assume in this case, just for the sake of working this through, this is the way I work the example, that this actually takes a total of 4 hours, because basically somebody's got to call the utility. Utility has to find a crew to dispatch to the field. The crew is going to go out into the field, and what's going to do is going to start riding up and down this line and try to find this location of the fault. They don't like just replacing the fuse unless they know exactly what caused the fault. And so Crew rides up and down the line. Maybe they have some problems finding the fault. If they know for certain that it was a temporary fault, then they go back up here and then they replace the fuse. And so that is what we refer to in this case as windshield time. And if this lateral is in like a heavily wooded area or whatever, this could actually be a very time consuming process. So anyway, we'll assume in this case for this line number 3, that this basically is kind of equivalent to doing a repair because it takes time to get the crew out there and to do all these different things that need to be done so they can feel comfortable putting that fuse back in again, because they just don't like putting it in unless they know for certain what actually caused it to blow in the first place. That'd be a safety issue. So if that were the case, if you had just 4 faults that were temporary in nature and they did turn out to blow the fuse, you'd actually get 4 sustained outages. You'd actually have to wait till the crew got out there. And then if it took 4 hours to find the fault and get comfortable with putting that fuse back in, that would give you like 16 outage hours, right? Where load B wouldn't be inconvenience at all because the fault on section 3 didn't even operate the circuit breaker. So B is actually isolated from that through the use of fusing. So what we can do is we can sum up all these different fault contributions for the 3 different fault types. Although for this temporary fault in line 3, we had that occur 4 times in a year. And what this is going to tell us is this is going to tell us for customer A and customer B how many momentaries we had, how many sustained operations we had, and how many outage hours that we would have. And this would just be for the temporary faults. We would do the same thing for the permanent faults. Now, a permanent fault, what's going to happen is the circuit breaker is going to operate. It'll try to reclose, but the reclosing will be unsuccessful because the fault's permanent. So eventually the circuit breaker is going to lock out open, right? And once that circuit breaker locks out, then all the customers see a sustained interruption. And in this particular case, what we said is that the mean time to repair was just 2 hours. It might be kind of a short period of time, but this is kind of what we're assuming in this case. So what this means is for A and B, they're both going to see a sustained interruption, and that's going to be 2 outage hours on the clock. Do the same thing for fault on line section 2, assuming the mean time to repair 2 hours. Again, 1 sustained interruption, 2 outage hours associated with that. And then for this event, if it's permanent, we're going to have 4 of these permanent events per year. It's going to have a 4-hour MTTR associated with it. For these 4 events, we're going to have 4 sustained outages and 16 outage hours. However, for load B, it would have no impact whatsoever because this section here is protected by a fuse. And that's one reason we use fuses on these circuits is if I have a lateral with a small number of customers, by putting a fuse on here, I keep a fault on this section from impacting sections of circuit that have much larger numbers of customers. So we can sum up all the permanent fault contributions. We have no momentaries. We just basically have sustained outages in this case. And these are the grand totals that we would have. And then you could have a passive failure. This line 3 could just fail open. We're assuming it takes 4 hours of repair. It doesn't impact customer B. And so we get 1 additional sustained outage at A associated with 4 outage hours. And you see this kind of adds up after a while. And so if I were going to total everything up for temporary faults, permanent faults, and also open circuit conditions, then as a function of load A versus load B, this would be the total count for the number of momentaries, the number of sustained, and the number of outage hours. And you see that the reliability at load A is much, much worse than the reliability at B. So now what we do is we can do the system indices. And so what we're doing is for the SAIFI, we're basically taking the number of events we're going to have, sustained events, we multiply by the number of customers in the numerator. We add to that the number of sustained events at B, multiplied by the number, I'm sorry, not B, yeah, it's B. Multiplied by the number of customers at B, we divide through by the net number, and we get 2.8 interruptions per year. You see it's nowhere near 11 because that was just associated with a really small customer count. And so I could have these pockets where I have really high number of operations, but might not impact my number that much because of the weighting, because we weight all customers equally. For SAIDI, you do the same thing. Got 50 customers, they're going to have 40 hours. I got 500 customers that have 4. So I multiply these terms and add them, normalized by the total number. That gives me 7.27 hours per year. And then for the MAIFI, we just focus on the momentary events, and we get an interruption number as well. And so this is kind of a baseline number that we could use for figuring out, well, what would be the benefit of different improvements. And what we would see then is we would see these numbers change when we make improvements to this particular circuit. So we can also get the number of operation counts if this is important. The circuit breaker operates 4 times. It's got 2 lockouts. We got 8 operations as a fuse in this case. And see, we got a lot of fuse operations and not so many circuit breaker operations. So I can put all these values into a table talked about before. I can get the grand totals for all these different events. And then by looking at the impact of customers A and B and weighting by the number of customers, then what I can do is I can get my total counts by customer, and then I can use my formulas from my SAIFI, SAIDI, and MAIFI for getting my initial net indices in. And so I think the table approach, this is usually what I ask students to do for homeworks and exams. It may seem kind of tedious, but it's very easy to make a mistake if you're going through and you're not correctly doing the bookkeeping. And so this table here is just a nice method of just keeping everything straight. And if you do make an error, then usually I could see in the table, like the fact you have a couple table entries are off, as opposed to if you just got these numbers, it'd be hard for me to tell where you made the mistake at. So you can see in this example here that the SAIDI number is really high. SAIDI number is like 7.27. That's terrible. You saw normally US customers would expect 2 hours per year. So this is like 4 times higher than normal. The SAIFI number is not too bad. The MAIFI number is not too bad. MAIFI number is still low. So you'd wonder, well, is there some way I can get a trade-off here between SAIDI and MAIFI? So if I'm willing to take more MAIFI events, could I get that SAIDI number down? And that's what we'll talk about next in part 2. And we kind of start to go through some more examples on this. So as far as references, the methodology that I'm using is from Richard Brown's book, Electric Power Distribution Reliability. I worked with him for a while when we were both with ABB. And so he actually developed a lot of these approaches initially for his PhD dissertation. He kind of kept working on this once he started working in industry, and wrote a number of different simulation programs around this. And so this is all based on material from his book. Tom Short has a lot of good background information. And then if you want to see like how programs like that ICE program from DOE work, there's a couple papers with Mike Sullivan as a primary author, where he talks about doing all these surveys in order to get these valuations. What's the cost of reliability? And there were some initial efforts like in the 2000 era, and then this was kind of updated like in 2015. And so these papers talk a little bit where the numbers behind the ICE calculator come from. All right. So what we'll do then in part 2 is we'll continue on with these examples, and I'll just go through a lot of different scenarios, and eventually you'll start to see some patterns for how these calculations are done.